This is a universe. Not ours, but one that looks uncannily similar. A vast expanse, filled with galaxies, stars, and worlds, all dancing to the same fundamental laws of physics we measure here on Earth. For billions of years, it stretches outward, as the fabric of space itself expands and carries its countless galaxies further apart. But in this universe, balance eventually shifts. The outward drive of expansion slows. Gravity, patient and relentless, begins to take the lead. The growth stalls, halts, and then reverses. Space contracts, galaxies rush inward, and the universe begins its long collapse. Everything is pulled closer and closer until it approaches the brink of a singularity, a point where space and time themselves would seem to end. Yet instead of ending in an infinite point, something extraordinary occurs. At the very edge, quantum rules intervene. The collapse halts, it rebounds. From that rebound, an entirely new cosmos bursts outward. In this story, the Big Bang was not the beginning at all. It was a transition, a rebirth. According to modern cosmology, our own universe began 13.8 billion years ago in an event we call the Big Bang. From a blisteringly hot and dense beginning, space expanded, cooled, and over time gave rise to galaxies, stars, and eventually life. Einstein's general relativity, combined with the standard model of cosmology, explains some of the grandest observations we can make: the cosmic microwave background, the faint afterglow of that early fireball, the cosmic web of galaxies stretching across billions of light years, and the surprising fact that expansion is accelerating today, powered by something mysterious we call dark energy. And yet, enormous mysteries remain. Dark matter and dark energy seem to make up about 95% of everything, but their true nature is unknown. Could there be a simpler explanation, one that avoids hypothetical particles and invisible forces? A story written only in the physics we already know. A team of scientists at the University of Portsmouth suggested exactly that. They proposed that our universe may have formed inside the depths of a colossal black hole, itself nested in a much larger parent cosmos. The idea is bold yet strikingly straightforward. What if our universe was born the same way a massive star collapses to form a black hole? When stars die, gravity overwhelms them. Some collapse into white dwarfs, supported by electron pressure. Others become neutron stars, held up by neutron pressure. But the most massive collapse completely, forming a black hole. The Portsmouth team asked, what if an entire region of space-time could collapse in the same way, then rebound into a new expanding interior? Remarkably, quantum physics already gives us a mechanism. Identical particles, like electrons or neutrons, cannot occupy the same quantum state. This rule, called the Pauli exclusion principle, creates a resistance whenever fermions are packed too tightly. That resistance is known as degeneracy pressure. It's what prevents white dwarfs from collapsing further. It's what holds up neutron stars against gravity's crush. Now imagine that principle scaled to a collapsing universe. As everything contracts to extreme densities, quantum pressure pushes back. The harder gravity squeezes, the stronger the resistance becomes. At some limit, collapse halts. Instead of an endless fall into singularity, the universe bounces outward. For anyone living inside that newborn expansion, it would look exactly like the Big Bang. Now, before we go further, if you're enjoying this journey into cosmic origins, make sure you subscribe to Quantum Leap. We dive into mysteries like this every week, and your support helps keep the cosmos within reach. So, how is this idea different from earlier bouncing universe theories? Many past models rely on speculative new fields, particles, or unknown physics. This one tries to stay within the tested boundaries of relativity and quantum mechanics.
Of course, we don't yet know what matter truly does beyond an event horizon. Observationally, black holes hide their interiors from us, But it's not unreasonable to think quantum effects prevent singularities from forming at all. Rather than a breakdown of physics, perhaps there's a new beginning. If this bounce picture is true, there could be survivors, ancient relics from before our universe's birth. Primordial black holes, exotic compact stars, or even traces of older structures could remain embedded in our cosmos. Discovering them would be compelling evidence. And intriguingly, observations with the James Webb Space Telescope have already spotted surprisingly mature galaxies far earlier than expected. These discoveries are difficult to reconcile with the standard model, but easier to explain if black holes in the early universe helped seed their rapid growth. Another thread of evidence may come from the way galaxies spin. In a perfectly random isotropic universe, we should expect spiral galaxies to rotate clockwise and counterclockwise in roughly equal numbers. Yet, some studies suggest that large regions show a preference for one spin direction. If confirmed, that kind of large-scale asymmetry could be a fingerprint of how our universe rotated or unfolded inside a larger black hole. To understand this better, we need to revisit the physics of black holes themselves. When matter collapses under gravity, it creates an event horizon, a boundary beyond which nothing escapes. From the outside, anything crossing this horizon is lost forever. But inside, relativity allows an entire space-time region to exist, one hidden from the parent cosmos. Black hole cosmology, sometimes called Schwarzschild cosmology, takes this seriously. Maybe our observable universe is the interior of one such region. Think of it this way. The standard Big Bang model begins from something we call a singularity, a point of infinite density. But the mathematical center of a black hole looks very much like the same thing. If our universe is the interior of a black hole in a parent cosmos, the Big Bang wasn't an explosion into emptiness. It was the rebound of collapse, creating a new expanding interior. And here's a breathtaking implication. Every black hole in our universe might itself give birth to a new cosmos. A cosmic tree of life where each branch is a universe budding from another. Over countless generations, the universes most likely to persist are those whose physical constants support stability and black hole formation. This could even explain why the laws of our universe appear so finely tuned for complexity and life. Entropy adds another layer. Black holes possess immense entropy. Their surface area encodes staggering amounts of information. If black holes are universe generators, their entropy could correspond to the richness of possibilities inside, including entire galaxies, stars, and civilizations. Extensions of relativity deepen the picture. In Einstein-Cartan theory, space-time is not only curved but twisted, influenced by the intrinsic spin of particles. At extreme densities, torsion can generate a repulsive force, preventing singularities and triggering a bounce. Rather than collapse to nothing, a black hole's core could rebound, birthing a universe inside. If our universe began this way, the Big Bang was not an explosion from nothing but the recoil of a cosmic bounce. An event seated in expanding space, hot and nearly uniform, just as we observe, but with subtle fingerprints, patterns in the cosmic microwave background, unusual distributions of primordial black holes, or gravitational waves from the bounce itself. Future experiments may reveal those signals. There's more. Studies of large-scale cosmic structures suggest possible anisotropies, patterns or alignments in the distribution of galaxies. These hints challenge the cosmological principle, which assumes the universe looks the same in every direction. If anisotropy is real, it could point back to the geometry of a parent black hole. Of course, extraordinary claims require extraordinary evidence. Some impossible galaxies may simply result from calibration errors or misinterpreted data. Hints of galaxy spin alignments could fade as more surveys accumulate. Even our local benchmarks, like the Milky Way's own rotation curve, carry uncertainties that ripple through cosmology. Science advances by testing and refining, not by seizing every anomaly as proof. Yet, regardless of outcome, the universe is stranger than we imagined. The idea that the Big Bang may have been a bounce inside a black hole pushes us to ask better questions, and better questions are the lifeblood of discovery. Picture it. a cosmic family tree. Each black hole, a doorway, each doorway, a new interior universe. Some collapse quickly, others expand for billions of years. Somewhere along one of those branches, in one of those interiors, life emerges, builds telescopes, and wonders how it all began. If the bounce story is true, then our universe is not the first, and certainly not the last. And if it isn't true, the search itself still transforms us. We learn more about dark matter, dark energy, and the rules that govern space-time. We sharpen our models, improve our measurements, and expand our imagination. This is Quantum Leap, and if you've stayed with me this far, you're part of a community that loves daring ideas and testable mysteries. So, what do you think? Could our universe really be the inside of a black hole? Drop your thoughts in the comments and let's debate it together. If you enjoyed this journey, hit subscribe, join us for the next leap, and keep exploring with curiosity and courage, because in the end, this is your space to wonder,